The theme of this session was on spatial data and how spatial data can be used to help people deal with government statistics. Certainly from the professional statistician, economist point of view, people who use federal statistics, they like to use spatial data because they can see patterns and work in combination with the system to apply their own perceptual reasoning to discover trends and see patterns that then can be further investigated.
Our long-term and overall goal is to provide a proactive mechanism for drought risk management that policy decision makers, government agencies, and individual producers can use to be instead of the usual crisis mode after the effect.
Well, in general, there are three reasons I think that they've not been able to solve the problem. One is that the kinds of data that we're looking at, to answer the problems, it's necessary to compare data across different federal agencies, and there are often barriers in place that prevent the agencies from sharing the data so that outside units like universities can help them solve that problem. In addition, many of these agencies don't have the expertise in place to develop graphics. They may have large teams of statisticians or other analysts, and so we're focusing particularly on the graphic end. And then third, we're particularly interested in the usability of these tools, and we have some expertise in doing cognitive research and usability analysis that is useful for these agencies.
The drought risk management problem is a hard problem to solve with the current methods that the government agencies have had. It is something that needs new spatial and temporal analysis techniques to do. In order to solve those new techniques, we need computer science research. The agencies we've been working with do not have the staff in-house, and in fact they've been experiencing staff reductions in the last few years. So this digital government project is able to bring together the computer scientists that are necessary and also provide the agencies that need to have this problem solved.
The main problem that I have looked at is trying to understand how spatial variables relate. And in my other work that's been sponsored by the NSF on multivariate methodologies, I've been looking at density estimation problems. And what I've been able to do is specialize that work to spatial data and particular maps. And the reaction from the collaborators has been very positive.
Well, we are trying to transit or make a transition from artificial intelligence to actual application. So we are building what we call a computational ontology or an information model of items and knowledge and things and concepts that exist in the maritime domain. We are trying to use that to create something that we call MIML, or Maritime Information Markup Language, and we are going to use that to enable, as I said, smarter programs that deal with maritime information.
It seems to me that every day when we are faced with statistical data, we often get contradictory information. It seems one day coffee is good for you, the next day coffee is bad for you. And what I've found is that the noise in the data, when you try and relate cancer mortality to other variables, really makes it very hard for humans to understand. And so our methodology gets rid of what I call the false positive problem, which is sort of spurious correlations that aren't real. And on the other extreme, we are able to find trends that are not instantaneous but slow over time. For example, the Firestone tire problem wasn't an instantaneous problem. It was something that people just didn't see because the change was so slow. Our techniques address both of these extremes.